Hello friends, I'm Nikita and you are watching Prepare for GATE. In today's topic, the content of our topic is discussed in two subjects of our GATE examination, that is electronic devices plus analog electronics. Now let's look to the content. The content is, this is the syllabus for the electronic devices. The content to be discussed today will be BJT. Now BJT is a subject matter that is widely asked, a question of 1 marks or mostly 2 marks question where you need to solve the whole problem is being asked in GATE examination over previous years. So we'll take a good look into how the BJT functions. Now let's first discuss about the fundamental of bipolar junction transistor. As the name suggests, bipolar, it is two poles. The BJT is a basic three-terminal device where the controls the output current. The two PN junction connected back to back, that is one forward biased and other reverse biased. The current, emitter current, base current and collector current are the respective regions current. The forward bias voltage is connected across the terminal emitter base and the reverse bias voltage across the terminal collector base. The two PN junctions form two depletion layers, each known as emitter junction and collector junction, where the width of the reverse bias collector junction is greater in comparison to the forward bias emitter depletion layer. The current entering through the terminal E causes electron-hole pairs generation. The majority carrier in P region and P- region is hole substitute constituting the emitter current IE and the collector current IC in the collector region. The majority carrier in base region is electrons forming base current. Now this was the basic about the PN junction. From this diagram we can see that WB is the width of the N region, P, or we can say P plus. Emitter region is always heavily doped with acceptor ions. What is acceptor ions? We have already discussed. They are the P-type ions having, no, they are not the P-type ions. They are the P-type ions means that they have 3 valence electrons in their valence shell and they can accept 1 more electron, or that's why they have majority of holes as their charge carriers. IE is the emitter current going into the emitter region, base current going away from the base region, collector current again going away. Now you can see that the emitter and the base region depletion width is less in comparison to the base and collector, because base and collector region is reverse bias, and from the formula is reverse bias, right? And we know the width is directly dependent on the biasing of the two junction, and emitter and base region is forward bias. That's why their depletion region is less, as the majority carrier from emitter region crosses to the base region and becomes minority charge carriers, and only minority charge carriers can be passed through this depletion region. For this region, There will be the majority charge carrier in p-type, but in n-type there will be the minority charge carriers. And being minority charge carrier in n-type, they can easily cross the depletion region. Here they have large velocity that helps them to cross this thin depletion region, and here we already know from our previous lectures that the minority carriers are unaffected by the width of the depletion region. So in this case they don't require a much energy to cross collector-based depletion region, and hence they can be partially transferred to the collector region and form this and complete their loop. So we'll next see how the currents in BJT are derived. Okay, before that, a good PNP transistor is one whose base width is less than the diffusion length. Diffusion length is actually the time is the length or the penetration when the electron crosses a region and before combining with an electron hole pair travels in the other opposite charge carrier region. Suppose in our earlier example, when the majority charge carriers in P region, such as holes, transferred from P region to N region, then the length covered by the hole in N region before combining with an electron is termed as a diffusion length, which is equals to the diffusion constant and tau p. Tau p is the time taken by a charge carrier. Such the emitter region will diffuse to the collector diffusion without recombination in the base. This property is shown by a good PNP transistor. Thus, the majority of holes penetrating the base region are transferred to the collector region. The base current substitutes electron for the excess hole charge. However, the base region being lightly doped and narrow in width, few electron pair hole pair recombination take place. The base current is measured in microampere. The base to emitter collector amplification alpha is equals to IE upon IB, and collector to base current amplification beta is equals to IC upon IB. Now the common relation between beta and alpha is beta is equals to alpha upon 1 minus alpha. Now here you can look at the different currents. In the diagram I have shown you that these diagrams I have taken to give you a better presentation of how actually the currents travel inside a BJT. The emitter current is crossing the emitter base region, having more number of width, larger width in N region as compared to P region, because N region is lightly doped in comparison to the P region. Similarly, in collector to base region, N region is again lightly doped in comparison to collector region. I is the whole current leaving emitter region. IC is the whole current leaving base region or entering collector region. At equilibrium, the Fermi level is flat and the band diagram corresponds to that of two back-to-back p-in junction. But for a forward bias and reverse bias collector, the Fermi level splits up into two. the excess hole concentration at the edge of the emitter depletion region becomes del PE. Okay, that is the change in the majority charge carriers, that is hole. The corresponding concentration at the end of the depletion region on the collector side of the base region becomes del PC. We can calculate del PE and del PC by this formula, where Pn is the total charge carriers in both in emitter region, exponential to the power E Q E B slash KT by Q minus 1. We can also write this as if the emitter junction is strongly forward biased, that is VEB is greater than KT by Q or VT, and strongly reverse biased, that is VEB is less than 0. Then we can reduce the earlier equations to respective equations like Pn e to the power VEB slash VT, or the change will be equals to minus Pn or minus the original current. Now, the total excess hole concentration in the base region will become IP will be equals to minus QADP diffusion constant A area Q del differentiation of dpxn o slash dxn, and the charge is 1 by 2a wbq del p. If you look at this diagram, you will clearly see how the charge carriers from one region to another region move. They have mostly considered that the minority charge carriers in each region. If you see, the minority charge carriers in P region would be the majority charge carriers of N region. The electrons, when they travel or crosses the emitter base region, they decreases with an exponential Np plus del Np and maintains at Np. When the holes from P region crosses to N region, they decreases with almost a linearity Pn plus del Pxn, and the base collector they increases to N. Okay, you can keep this diagram as your reference because most of the time quite a lot number of questions are being asked over the charge carriers. This concept is important to remember because in this you will actually see how the charge carriers crosses these junctions without considering their fields, respective electric fields. I won't say that they do not completely negate the effect of electric field. However, because of their design, they help to overcome the electric fields present within, and the charge carriers can move through the device. The